Couchbase is a modern, multi-cloud-to-edge, SQL-friendly JSON document database for building applications with agility, performance, and scale. If you're new to Couchbase and would like to learn more, the Couchbase Developer Portal is the best place to start. It's loaded with tutorials, videos, and documentation, as well as best practice tips, quick start guides, and community resources, including the Couchbase Developer Community Forum. Are you ready to get started developing on Couchbase? Visit couchbase.com/HanselMinutes. That's couchbase.com/HanselMinutes. Hi, I'm Scott Hanselman. This is another episode of Hansel Minutes. Today I'm talking with Eric Newcomer. He's the CTO of WSO2. How are you, sir?
Pretty good, thanks. How about you?
I'm living the dream here, remote, in the middle of a panini, as we say. But I am getting a chance to talk to a lot of cool people here on the podcast, and I'm learning a lot. It's definitely been a time where we could turn inside ourselves. We're stuck at home. So there's a lot of reading, a lot of research, and a lot of learning. I hope you're getting the chance to do the same.
Oh my gosh, I thought last year we were done with Pandemic Central here in New York City, but it seems like it's coming around again. Not as bad as last time.
Yeah,
but
it does feel like we've lost a year, and now we're going to go and start it again. But hopefully, we'll be done soon.
Yes.
So you work at WSO2, Web Services Oxygenated, is what you told me that it means.
Exactly.
Which is pretty cool because you've been working on web services. That's been a passion area for you for a very, very long time. And I worked on web services and SOAP and all that stuff as well. But things are different now.
Sure. I remember when it started back in 2000. I was CTO at Iona then, and I had worked at Compaq just before then by way of the digital acquisition. And one of the things I was working on was a Microsoft partnership. So when the topic of SOAP came up at Iona and the management said, well, Microsoft has this, we don't really know what it is, I called a few people and got us access to it. And we signed up, and we were actually the first vendor to publicly commit to standardization of SOAP. And then we helped submit to W3C and the whole thing. So that was a very interesting time. We pivoted we were at the Corba company then. We had to become the web services company, and now we're out of business. So I don't know what that tells you.
So SOAP meant Simple Object Access Protocol, but whether it be web APIs today or SOAP then, all of this is trying to get transactions and to do work over the internet and over the World Wide Web, which was a thing that, if I recall, Tim Berners-Lee thought we would just be basically passing academic documents around over.
Yeah, that was the original invention, was to share academic documents over the internet. And I think no one expected it to be used for transaction processing. Certainly I didn't when I first got involved. I tried to hand off the SOAP spec actually to somebody else at Iona because I was the transaction architect. I was busy doing the object transaction monitor, the OTS standard. And they said, no, where do you think you are at Digital anymore? It's a small company. You have to do this. So I did this both for about 2 years. Eventually I ended up writing the WS transaction spec to kind of merge the interests. But then it kind of shifted over more to web services.
Mm-hmm. Is all of this that we have today in 2021 built on hacks, or is it just abstraction layers? Should we be worried about the underlying infrastructure, or is it just that we're building smarter and we're learning about our mistakes and building correctly? Or are we built on top of something that Tim Berners-Lee could have never have even thought about?
Well, I hate to say this, but I sometimes find it amusing that Tim tries to fix the web that he created, even though long ago it got completely out of his hands. So I think the original web did definitely create the foundation, but where it's been taken has been in completely different directions than originally was intended.
Mm-hmm. So when things are the term ACID, the acronym ACID, is used a lot to talk about a transaction, the properties of a transaction, atomicity, consistency, reliability, and durability. I assume that this is still the gospel, for lack of a better word.
That's a conceptual way to put it, but it's certainly a way of evaluating what's going on and determining whether you're doing the right things or not for your business transaction. Absolutely still one of the tests. I've been a transaction processing guy most of my career, and that's kind of how I view things. I was kind of looking at some notes, or making some notes for today, and I realized that actually the first time I saw a computer was in 1974. That was my first time I was doing coding, back in college. And I was telling one of my cousins about this the other day, going, what are you talking about? 1974. Just had a mainframe computer in one room at the college. And when you were a student, you had to go take the system disk off that they used during the day for administration, put the system disk that you used for student projects on, and punch in the address on the system disk of the bootstrap code that would start to load the system. And we created programs on punch cards and ran them through. I was just thinking about this because back in those days, the mainframe was in a room and you went there and you worked on it there. You didn't have a computer in your pocket. You didn't have a network. You didn't have, some computers had dial-up, but there was no networking. Everything was just this mainframe-oriented central control model that you went to as a person. Mm-hmm. And you think about today, the data centers that you have today with Google and Amazon and Microsoft, Facebook, everybody, these are huge, thousands of computers and hundreds of data centers. You can't even go in there if you wanted to. They're all protected by security. And you have no idea where your program is running. Probably you don't even want to know. But it's very interesting to me how things have evolved from those days when you had one computer running one program. That's in those days, you pretty much engineered an application to run on a mainframe. You engineered the mainframe for the application in many cases. I was just recently working at Citi, and they still have some of these things going. They were created 40, 50, 60 years ago. They're a very special purpose. But then how do you change this, scale up, central control, everything's in one room, everything's in one box, disk, CPU, memory, all right there within immediate control to this model where you've got hundreds of thousands of computers around the world trying to collaborate on an application across the network. How do you change your thinking? How do you approach things differently? How do you make sure, as you were saying, you still have the right properties to make sure your transactions are done correctly, even though the world has changed so much? And I do blame the web. Maybe blame is the wrong word, but I think the web is what's one of the big things that's created this change.
This might be a weak analogy, but most of my analogies on the show here tend to be a little stretched. But if we imagine a room with a mainframe in it and we shrink that mainframe down to a Raspberry Pi or an iPhone or a laptop or something small, some of the metaphor works because there's a heck of a lot of power in those tiny devices. Would there be any difference between a networked mainframe and thousands of them all over the world talking to each other and networked Raspberry Pis and things like that, or networked phones? I mean, is it just simply that it's now miniaturized and then there's the speed of light to think about?
Let's look at it from this perspective. When the web first came out, companies, when I was working at Digital Equipment in those days, we looked at websites as something we bolted on to our internal systems. Mm-hmm. We ran all our internal systems to run the company. Sure, we had DARPANET access, but that was kind of research networking. We had our own internal DECnet that we ran the company on. And we thought about porting between that and the outside world is how we were doing the internet. But we never thought about the web as a way to design and build systems. We were designing and building our operational systems, our TP systems, for how we would run our own company inside our four walls. And connecting it out for the network was something sort of a secondary consideration. It wasn't really part of the design. It was like a bolt-on. You take a web server, you bolt it on, and you have this now a portal between what you're doing inside the company, what's going on in the outside world. But this whole thing was inverted by Google. When they created their data centers about 20 years ago, when they founded their company, they put the web design inside the company. They created their data center based on web design principles. So there was not a bolt-on. There was not this kind of impedance mismatch or this disconnect between what's going on inside the company, what's going on outside the company, as there was in the original days of the web when you thought about it as, this is just something I connect to. It's not how I run my systems. Google came out and made a lot of assumptions that were different in terms of how I'm going to run my data center. I'm going to run it as a huge web farm. I don't have a web server bolted onto my enterprise apps. I have a web doing everything, a data center that does everything. And that has huge implications for everything. And to me, that's how the cloud got started. Microservices got started, big data, DevOps, all the modern trends that we're all trying to adjust to was created because of this change, the inversion of thinking between the web is something I bolt onto my systems or the web is my system.
That is a really great way to think about it. The early banking systems that I worked on, we thought about the mainframe as being its own island, and then we had a broker that would go back and forth between it. But it never felt like it was participating. It was the authoritative source, but the web APIs and the SOAP APIs, and then later the JSON APIs that were on top of it were just spackle. They were putty.
It's adding on to these connectivity things as opposed to designing your system around that concept. And I think that's been a sea change. And that's one of the reasons why things have had to be reinvented. It's why we have this whole cloud native computing concept. Instead of the old scale up mainframe, we've got these scale out systems. We've got auto scale, we've got auto resiliency, but you have to design for it. You have to design your apps as if they were on the web, operating independently. And when we were first doing distributed computing at Digital, and I'm sure Microsoft and a lot of other companies doing, trying to extend the wire out from mainframes, maybe trying to take some of the workloads off of mainframes to distributed systems, we were all thinking, hey, we've got to provide all the exact same capabilities that are on the mainframe. We have to stretch that wire so the distributed systems are participating in the distributed transaction just as if that transaction were part of the mainframe in that room. Now we've got a machine in another room, but we're just going to assume it's all part of the same sphere of control, all part of the same environment, and it's going to work the same way. And with the web, you have a different assumption. You don't have these shared connections. You don't have a shared session state. HTTP omits that on purpose. You can see it in Roy Fielding's thesis that they have no shared session state on purpose so they can scale up in the wide area network. So that's another one of the big factors that's come in and changed everything. As we used to think about computing as local area networks with a wide area network bolted on, as we were just talking about. But the web was designed for a wide area network. HTTP was designed for that. This is why we need programming abstractions that work better for this kind of distributed computing environment where you're working independently on thousands of small systems instead of trying to coordinate all your work into one big system as if it were one extended mainframe.
Security threats in cloud-native environments move fast, which means that security teams need to have the same visibility into their infrastructure, network, and applications as developers and operations. With Datadog security monitoring, engineering teams can easily detect malicious activity in real time before it affects their customers. Use out-of-the-box detection rules and detailed observability data in one unified platform to investigate security attacks. See it in action by signing up for a live security demo and receive a Datadog t-shirt by visiting datadoghq.com/HanselMinutes-security. That's datadoghq.com/HanselMinutes-security. In the notes that you sent me, you said something really interesting I want to dig into a little bit because it speaks to what you just said. You said the wire is too tight. What does that mean, the wire is too tight?
Well, you have too many dependencies that you introduce between programs. So if you are connecting up programs for a transaction, let's say, and you've got part of your transaction work on the mainframe and part on a PC, you're stretching the wire between those two. So if you coordinate data changes on the PC or the Linux server with data changes on the mainframe and something goes wrong, you have a hard time, getting everything back in sync. Whereas if you assume that the systems are working independently and they only exchange state in a sort of disconnected way and how they're responsible for their own updates, you have a different type of failure management, different type of resiliency that you can create. It's a little bit like, this old distinction we used to make between the servers that were read-only and the servers that were read-write. If it was a read-only server, you could have a whole pool of them. It wouldn't matter which request it went to. You'd always get the same result. But if you had a read-write server and you started your update transaction, you had to go back to that exact same server. You had to have these sticky sessions to make sure that you got the data back in the right place where you locked it and kept it available for the next message in that transaction. So a typical update pattern: read the record, lock the database, modify the record on the screen, send it back up the database. That's stretching the wire, and the wire gets a little too tight when you have hundreds and thousands of these things going on at the same time. You want to have your transaction servers acting the same way as your read-only servers, that your message can go to any one of those pools of servers and just scale them up and down dramatically. But you have to redesign your apps to do that. You might need a new programming language syntax, such as we're working on at WSO2 with Ballerina, to make that all intuitive and make the change easier to deal with.
And understanding the business person's problem, because the business person always says at the simplest level, I need it to be real time, I need it to be perfect. But if it's a Facebook like and I hit like and someone doesn't see the right number of likes, it doesn't matter, right? It'll eventually be consistent, but it's not a big deal.
Yeah. It's such a continuum. It's a trade-off discussion. It's not absolutely everything has to be locked down and changed. Eventual consistency, for example, came out of this concept of, now I've got my whole application designed as if it were on the web, which Google is pioneering this with the cloud native commodity data centers and all this kind of stuff. running enterprise workloads on consumer grade hardware. It's such a crazy shift, but they did it. Now everybody's doing it, and we have to engineer for it. We have to re-engineer. We need new tools, new programming languages to help that re-engineering, which is some of the things that we're working on. But you have this system where, instead of this, kind of assuming everything's all working together to achieve a common result, you have things that are working independently that can achieve a bigger result by working independently, scaling up, and not having these dependencies of these tight wires anymore that kind of limit what you can do. And the eventual consistency is one of those. And this came out of the idea that, in the old days, as we were just talking about, if you wanted to get a transaction recorded and perfectly done, you put it on stable storage and committed it with ACID properties, and then you return control to the application and say, hey, I got your data. It's safely on storage. It's a disk. Don't worry. You can do whatever you want now. We've got your update. We've got your transaction. It's safely stored. We return control to your ATM or whatever and say, we got your request. It's safe. With eventual consistency, instead of that, the web companies were finding this took too long to go all the way to disk and write in stable storage. They wanted to just write to memory and go back to the user and say, hey, yeah, we got it. But that's risky, right? Memory is transitive. It can evaporate when you lose power. So you replicate memory. And you think, okay, I've got enough replications of this update and enough servers. And now we're in this big server farm of hundreds of small PCs, and we're writing out these updates multiple times to multiple parts of memory on different systems. And now we think we have enough because we have 6 or 8 of them. They're not going to all fail at once. There's a little bit of a recovery issue because replication is not instantaneous. Just as a side issue, I used to work at Citibank, and I would tell people about this as a better way to improve latency on some of our systems. They would say, but there's a risk of failure. I said, okay, so what's the risk of failure in our current systems? It was actually pretty much higher than that. But they wouldn't like to admit it because of this assumption that things don't fail. We're going to engineer failure out. And Google turned that on its head as well. They said, no, things are going to fail. We're going to work around that. We're going to buy consumer-grade components. They're going to fail. We know they're going to fail. We don't care. We're going to make copies of everything on different computers and just keep going. So you get this copy in memory, and replicated memory is failure window, but it's a trade-off, right, between that and another type of failure that's a larger scale failure. It's an incident that takes your system down and you're out of business. You're off the air versus, you lose somebody's transaction. You come back and apologize and say, sorry, we lost your order, or the forklift ran over it, or, whatever, for an excuse.
When I was working in large banks, I always thought it was funny that they would say, we can't risk failure, but then they would take the entire system down every 28 days for maintenance. And that's arguably a fail. The thing has been down from 11 p.m. to 2 a.m. or the bill pay window closed and, your bill got pushed a day. Like, those are all failures, but they don't acknowledge that they are.
Correct. It was such a different world of assumptions. And that's, again, what's been changing with, the web coming in. There's so many. When we were working on this whole stream of distributed computing, kind of based on this mainframe scale-up model, extending the wire, we never imagined that this system of sharing documents, this SGML thing that used to mark up your documents and publish them and format them, all this stuff, that would ever be used for mission-critical TP systems. And yet, here we are.
Mm-hmm. So you and your team argue that the programming styles, the languages, the ones that we've inherited, the ones that we've created, don't necessarily acknowledge that all of these different things we just talked about, those network primitives, and that's why one of the things that you work on is Ballerina. Folks can see it at ballerina.io, and we'll put a link in the show notes. So this is a language that acknowledges all of these things that you say are fact, right? Like network primitives should be baked into the language, and latency is a thing. The network exists, the wire exists, and that is known at the language level. Is that right?
Exactly right. Instead of, to use the old bolt-on analogy, if you look at a Java program, you're kind of bolting on all the network libraries. If you look at dealing with HTTP requests in Java, you've got this complex code to put together the string and parse the results, and how are you going to send it out? It's not what Java was built for. It was built for programs in a single address space and programs written in Java that it called the Java interface and Java libraries and all this stuff is not really built for this widely distributed computing environment where all the assumptions about how things work have changed. And that is really what we're working on. I wouldn't claim we're done with it, but I think if you were to look at the HTTP abstractions, and as a matter of fact, for the GraphQL abstractions, I think you would see what it is we're trying to accomplish in terms of making things intuitive and simple for the type of distributed computing that's become the reality now that the web model is really what everyone's using.
Right. Well, it's interesting if you draw the parallel from before about bolting things onto mainframes, and whether it be C# or .NET, where here's the HTTP library or Go or Java or whatever. You're right. There's this central thing that is atomic, whether it be the mainframe or the CLR or the JVM, and then there's this library that kind of sits around it that is network agnostic, even though everyone knows the only one we're really using is HTTP.
Yeah, and if you look even a little further back, those languages were developed for greenfield applications. Java EE in its infancy was all about how do I start from a blank sheet and create a huge application all in Java. And certainly in the old days when I was first working, the big challenge was automating manual processes. It wasn't how do we stitch together all the stuff we've already created. And if you look at how the web was started, it was all about, here I've got my documents here that I'm doing my research on. Somebody else has got their documents there they're working on. We're not connected, but we want to share. So we set up this connection that's dynamic through the URLs, the links. And when you click on a link, it goes out, gets the document, brings it back, and it's done. And if you think about that as a different model for exchanging state and for assuming the type of applications you're creating, you can create your own application with these links out of the network that are kind of built in through the URLs, and somebody else is working on their application. They don't really have to coordinate anything except expose these standards. So in the way in which the web has contributed to this, they had created these standards that everybody was able to use to work independently. One of the things I was most interested about the web when it first came out was people could update their websites independently. And, we sort of take this for granted now, but back in the old days of Corba and web services and DCE and IDL and original distributed computing stuff, you thought, well, I have to coordinate the client and the server together to make sure all the changes are made on both ends to make sure this is working. And with the web, you don't have to do that. And that concept really carries through to cloud native computing and the things that people have to do to re-engineer their monoliths to microservices. If you really want to get all the benefits out of it, you've got to be able to allow these things to evolve independently. Microservices, one of their biggest attractions is independent evolution, but they can only do that if they're not stretching the wire, if they're accessible, if they have all their state, they manage all their state, there's no session-oriented state connecting them to another transaction or another security or anything like this. And it's such a change in thinking that we are going to need to reimagine not only our system software, which we're doing with cloud native computing capabilities, big data, microservices, Kafka, all these things that are coming out with this model, RabbitMQ. We need to change how we imagine our programming and how we stitch things together and how things are going to work together. And that's a lot of what we're starting to work on.
One thing I was impressed about when I was looking at Ballerina was that in VS Code, there's a plugin that allows you to look at the code that you're writing for your services, whether it be sending email or whether it be making a web service call. And then there's an associated view of that as a graphical environment. So basically a sequence diagram, which is like, I wish I had this in the 90s. I was at Nike drawing sequence diagrams manually and then later in Visio, but then translating them into the language that I wanted to use. You can look at Ballerina code as a sequence diagram and just kind of flip it over on its side. Like, here's the text version, here's the graphical version.
It turns out the solution to this graphical language compatibility thing is to put syntax primitives in the language to create the diagrams. In the old days, I remember even, Visual COBOL way back in the days, we were trying to create diagrams to generate COBOL, and it works to some extent, and UML works to some extent, but the round trip was never solved. Turns out, that was another thing we definitely worked on in Ballerina, and reason for it, we're really an integration-focused company, and if you're doing integrations, you always have to have a sequence diagram to kind of show everybody what it is you're doing. As you said, sometimes you'd have to draw them, hey, this is what we're going to build. Everybody says, okay, and then you go and build it. And our thought was, well, if everybody needs a sequence diagram anyway, why not just create it from the code? And then later in Choreo, we also were able to take the sequence diagram, change that, and generate code from it because we designed it to do that from the beginning. So that's something else that we think is a good contribution toward this.
So you said that previous languages were built with a greenfield in mind, but a lot of in a brownfield environment, they've already got .NET, they've already got Java. Ballerina is meant to interoperate with Java. You can call Java code from Ballerina and vice versa.
Oh, sure, yeah, it works. It works out of the box with Java libraries. We don't see it as a Java language. It's running in the JVM right now, but we're also creating a native version of it through an LLVM port, so there'll be a binary compatible compiled version coming out hopefully in a few months as well. So you have the option to run it in the Java ecosystem or to run it, perhaps with more efficiency in a native environment, because Java, as we're saying, was kind of, at the time it came out, it became popular as I remember I was learning C at the time, and it was like, okay, now Java's coming in, I have to learn something else, because we always thought there would be one programming language everybody was going to use for everything. It was one general purpose language to get widely adopted. Now I don't think we have that assumption anymore. I think we have the assumption in the industry that we're going to be having languages for specific purposes that allow you to do different kinds of work and create those different kinds of work more productively than using one language for everything. And Java, because of its origin, is not very agile for the cloud. There's a lot of efforts to try to retrofit cloud native computing into the Java ecosystem with Quarkus and MicroProfile and Micronaut, these kind of things. And our view is let's just design something from the ground up that is agile. This is why we're doing, we got the language going with Java. We're going to do the native version so it is agile, it's fast, you can deploy it in containers, Kubernetes. Something else we worked on in the language was putting in the metadata you need to create Docker files and create Kubernetes configs out of the language. Speaking of how helping with the cloud native shift, it's another way we're doing it. We're taking a little bit of the deployment aspect and abstracting that as well.
Yeah, and it's also, and I love this, it's a network-friendly type system. So, we learn in school ints and strings and date times, but why not JSON and XML as types that are baked into the language?
Exactly. Another assumption that has to be turned on its head. In the old days, you assumed that you designed the data types for the language that would allow you to do the work in the language that you needed to do. But now, with hundreds and your application running hundreds or thousands of computers, you need to think about data as what's flowing between those computers. And the data types that we put in are network data types. You create schemas in the language so you have the same thing in memory on the wire for JSON, for XML, and so forth. We really help with that as well.
Yeah, that's really thoughtful. In managed languages like Java and even C#, we're spending a lot of time brokering between one format and another, effectively serializing and deserializing. And since JSON is JavaScript, it's only JavaScript that gets it for free. Why shouldn't other languages get it for free as well?
Yeah. This is another old problem in the industry. Back in the day when I was doing COBOL, we had a set of data types that was great for report writing and for printing out things. And I told you I was learning C after that, and we had a whole set of data types that are great for pointers and memory management and system service calls and that kind of thing. And there was not a lot of compatibility in the data typing between COBOL and C. When you would try to stitch those things together, you had to create a brokerage, a serialization, a mapping. And that's a lot of the problem that people have in integration. Again, we're kind of coming from the point of view of an integration company, thinking about the problem in the web space, in the cloud space. We should be able to have the data types in the language that are needed on the network, as opposed to what are the data types needed for the language when it's running on its own. And this is, again, back to it's not a bolt-on anymore. It's just part of how you do things that this whole cloud native revolution is ushering in.
Do you think it's a hard sell to have a new language? Like there's always the whole argument of we have 12 standards, let's make another one. Now we have 13 standards. There's a lot of excitement around Go. There's a lot of excitement around .NET Core now that it's open source. Where does Ballerina fit into a crowded place?
We do get this. We get people saying, well, where am I going to find a Ballerina programmer on the jobs postings on LinkedIn or whatever? And that is a valid concern, but I think it's becoming less so because I think people are starting to see that multiple languages are coming out for different purposes. They're seeing Kotlin and Swift for mobile apps, and they're seeing Rust for replacement of C for system kinds of programming. There's languages coming out for math and for science and for ML and this kind of thing. So I think we are getting used to the idea that there are going to be different languages, that people are going to have to learn different languages in their career. You can't just have one language that does everything. And intuitively, it doesn't really make sense that you would have one language that does everything now that this industry has become so broad and so all-encompassing. Back in the day when you just had a mainframe in one room, one language is probably all you needed, or maybe two. But now, a lot of different work, IoT devices out there, you probably do need a lot of different languages. I have a friend who's a very kind of high-powered developer. I showed him Ballerina, and he played around with it, and he said, one of the things he said was, I like the GraphQL abstraction. I think I could use this for some of my GraphQL services. So he had in mind he was going to use one language. I think he's a big Kotlin guy. Most of the things are going to be in Kotlin. When he comes to a GraphQL service, he's going to write it in Ballerina because it's just easier to do it that way. And so certain courses for courses, right? Certain languages are better for good different things. And if you get to the point of having the discussion and you can clearly show the benefit of taking the investment in learning a language, is going to make it easier and simpler for you to do a certain number of tasks more productively. You can make the argument that we're in that world now where it makes sense to take that learning curve. But yeah, it's an issue, and we do have high ambitions as well. We'd love to get this be an industry adopted language. We're going to work on that as well.
Well, the other great thing that's nice about Ballerina is that it integrates with all the stuff that people are already using, right? So if someone's like, I'm going to bring a new language and put it into our environment, it's like, well, does it work with Prometheus? Does it work with Grafana? Does it work with Jaeger? Does it work with Elastic Stack? Well, it actually works with all of those things. So it's not going to be hard to, you're not going to have to shoehorn this into existing systems because you can broker to other languages and you can plug into all of your external systems for observation.
We really tried not to rewrite all the things that exist to make it easier for people to integrate. Again, we're coming at this from the view of an integration company. And the origin of Ballerina was as an integration programming language that abstracted middleware. And the original thought was if you can create integration is programming. If you have its own world, its own black box, as it used to be, where you had to learn your own specific integration programming language, and you had to do your business logic in another language, why wouldn't it make sense to have one language where you could do both? So we thought, well, let's abstract this coming from the integration point of view, but also adding the logics you need for business logic. You could have one language to do both types of tasks.
Very cool. Well, it's an exciting time, and it's great that you're using the historical context that you have and the remembering where we came from to help define where we're going.
It's fascinating to me just to think about how far we've come I hate to think how many years it's been that I've been working on this stuff, and looking forward to see where we go next, for sure.
Very cool. Well, thanks so much for chatting with me, Eric Newcomer. He's a CTO of WSO2, and he works on many things over there, including Ballerina that you can check out at ballerina.io, and I'll include links in the show notes. This has been another episode of Hansel Minutes, and we'll see you again next week.